Okay, so for part 2 of homework 4-2 here, we'll pick up with questions 6, 7, and 8, and maybe get to 9 as well. So, question 6. The figure below shows a potential energy diagram once again for a 500 gram, so a 0.500 kilogram, right, particle that is released at rest from point A. What are the particle speeds at B, C, and D? Well, this one's hopefully not a bad question at all, right? It tells me it's released at rest from this location. And again, this is representing the potential energy, which they're using U, right? But it's representing the potential energy. So the total energy at that location, right, the total energy is 5 joules of energy. Well, unless they tell us otherwise, and we're assuming there's not any outside force, right? Unless they tell us otherwise, we're assuming there's no friction, air resistance, anything like that. And so what that tells me is the total energy would constantly be 5 joules of energy. So as the potential energy decreases, what happens? Well, some of that potential energy goes to kinetic energy, right? So that's really the key to this. Once you're comfortable with that, this question is very easy, right? Because at this location here at point B, if I want to find the speed, right, I'm going to use kinetic energy to help me out. Well, it started with 5 joules of energy. It now has just 2 joules of energy left for potential energy. So that means the remaining 3 joules of energy, right, are its kinetic energy. So at that location it has 3 joules of kinetic energy, which once I know how much kinetic energy it has, I can just do 1/2 mass times velocity squared, right? They gave me the mass for that reason. So I've got 3 joules equals 1/2 times another 1/2, 0.5, right? And then v squared, and I just solve for v. So obviously, just end up solving that, I get that to be about 3.46 once I rounded that off. So the velocity at point B is 3.46 meters per second squared. I use the exact same type of rationale for both point C and point D as well. So at point C, it has 2 joules of kinetic energy, right, because it has 3 joules of potential. So I use 2 equals 1/2 times, again, 0.5 times velocity squared, and I solve for that velocity. So the velocity at point C ends up being about 2.83 meters per second squared, or meters per second, excuse me. And then finally for part D, right, for point D down here, at that location it has all 5 joules are kinetic energy. So 5 equals 1/2 0.5 times v squared, and my velocity at point D ends up being about 4.47 meters per second. So anyway, hopefully this question pretty easy to work with once we've established, right, that relationship between energies. Question 7 here is a very similar question to that of question 6. However, it is kind of have us go the other direction, right? It does have us go the other direction. So what minimum speed does a 100 gram particle, so again 100 gram would be 0.100 kilograms, need at point A to reach point B? Well, if it's starting here, right, in order for this particle at point A to reach point B, according to this curve, it has to have at least 5 joules of total energy. Because in order to go up and convert to 5 joules of potential energy, right, it would have to have at least 3 joules of kinetic energy that it could convert to potential energy. So once again, that becomes the key. If I'm going to make it up that curve, I have to have at least 3 joules of kinetic energy. And so that helps me find the minimum velocity. If I have to have at least 3 joules of kinetic energy, then I can figure out what that minimum velocity I need to have is, right? Because I know that the joules here needs to equal my my velocity, and so that velocity would have to be at least above that minimum. So anyway, solving then this equation, just 3 equals 1/2 0.1 times the velocity squared, right? So solving for v, I get that it's 7.75 meters per second. So again, this represents the minimum velocity that the particle at point A needs to have. It could have anything more than that. So I would just say simply the velocity has to be greater than or equal to 7.75 meters per second. It does, however, ask for the minimum velocity, so you could just say the minimum velocity equals this as well, right? So either of those answers would be fine. This would be the range of velocities that would work. This would be the actual minimum velocity. Then doing the exact same thing for part B, right? Except we're going this time from point B to point A. Well, if I want to go from point B to reach point A, I have to have at least 5 joules of kinetic energy that I can convert to potential energy, right? In order to make it up that hill there, if you will, I've got to have 5 joules of energy that I can take advantage of. So the exact same type of relationship, I'm just using 5 instead of 3. So then solving for that equation, the minimum velocity that I need to have at point B would be equal to exactly 10 meters per second actually. So when you solve that, it ends up being exactly 10. But anyway, hopefully a pretty easy question to work your way through. Again, nothing too crazy on that, right? But definitely want to make sure you're comfortable with. Okay, so question 8 here is a pretty good question for how can we work with energies if it's in the form of a system, right? I know at this point you guys are all very, very comfortable and very good with working with energies if it's just a single block, right? If I told you a single block compresses into a spring, no big deal, you got it, right? But what happens if we have a system where we have multiple masses at play? How do we work with it then? Well, obviously you guys can read through this question, right? Make sure you're comfortable kind of identifying all the key figures here. But what's happening? So this picture is before it's been stretched at all. So originally this block is just resting on the ramp, this one's resting on the spring, right? Then they say that I've pulled the 20 kilogram block. It says it's pulled a distance of 20 centimeters down the incline. So I pull this down the incline, right? And then I release it from rest. So it's down the incline 0.20 meters, right? And then I release it from rest at that location. They want me to then find the speed once it returns back to this location. Okay, so I've got that system, I pull it down. Well, let's think about what happens, right? As I pull it down, what happens to the spring? Well, doesn't the spring also stretch then by 0.20 meters, right? That spring ends up then stretching by 0.20 meters. So we've got those measurements to work with, right? So anyway, how can we work this, right? How can we set up this equation, this solution? Well, the key is using energies can still work for us, right? So I'm still going to take the same approach I usually do. I know that if there's no outside forces, and once I release it, there aren't any outside forces, right? Now obviously to pull it down, I had to exert a force on it. But once it's here and then released, the only forces acting on it are the spring force and the force of gravity, right, which are all kind of part of this system. So as long as there aren't any outside forces, I know that the total initial energy would be equal to the total final energy. So all I really have to do is try to identify what types of energy it has initially and what types of energy it ends up with. Well, the key here is I'm going to define the spot to which this has been stretched at to be 0. So as that block is stretched down the ramp, I'm going to define that initial spot to be 0. And the reason I do that is then because the potential energy on that first block would be 0, right, because it would be at that height of 0. The kinetic energy of that first block, right, and really the kinetic energy of the entire system would be 0 because neither block is moving. They're released from rest, so they both start at 0. But I would have two forms of energy, right? I would have two forms of energy that I start off with here. I would have the spring potential energy as that spring stretches. I'd have the spring potential energy, and I'd also have the change in potential energy due to gravity as this block, the second block, has been lifted up. So I'm going to call that the potential energy 2 of gravity, distinguishing that this is the second block over here and this is the first block over here. So I've defined this height as 0 from where it's been stretched to, but then with respect to the spring over here, that one has been displaced upward, so I am going to define that potential energy due to gravity separately. So anyway, these are the energies that I start with, right? I've got the spring potential, I've got the gravitational potential. So hopefully you guys are okay with that. So then what energies do I end up with? Well, obviously the question suggests I end up with some type of kinetic energy, right? I do have some type of kinetic energy because they asked me to find the speed. So it's probably not 0, otherwise this is just kind of a sneaky or a mean question, right? But anyway, so I've got the kinetic energy. I know that's going to have some of that. And then other than that, what other forms of energy do I have? Well, after I release the system and it reaches the unstretched length, both the spring and the gravitational potential energy over here would be gone, right? Because the spring isn't stretched anymore, so that potential energy would be 0. And the gravitational energy that I defined over there would also be 0 because it's not been pulled above its original position, right? It's back to where it was originally at, which I'm defining as 0. So both of those forms of potential energy would actually be gone for the final measurements. But I do have one other form of energy, right? I have the change in potential energy for the block itself as the block goes up the ramp. So I do have the potential energy due to gravity of block 1. So really the moral of this story, what I do hope you're comfortable with as I go through this, and hopefully again all of the little bits and pieces made sense as we set it up. But all I did was I took each block separately really, and I considered what forms of energy act on that block, or what forms of energy does that block possess, and then I just related them through the entire system, right? I just said, well, block 1 has these energies, block 2 has these energies, and then afterwards the energies over here as well. So then at this point, it's really just a matter of breaking everything up and plugging in what variables I know. So again, the initial spring potential energy would be 1/2 kx squared. I've got the constant, and I've got how far it's been stretched, so I know all of those. The potential energy due to gravity would be mass times gravity times the change in height, which again, because I know how far it's been stretched, I know my change in height for that second block. So I've got that. The kinetic energy, I do have to be careful. The kinetic energy would be 1/2, but since both masses are going to be moving at the same velocity, it would be the total mass of the system. So it'd be mass 1 plus mass 2, whereas this over here was just mass 2. Right? And then times my velocity squared, which is obviously what I'm looking for. The potential energy of gravity would be just the potential energy of gravity acting on block 1, so it would just be mass 1. So it'd be mass 1 times gravity times height, where keep in mind the height wouldn't be the 0.20, but it would be just the vertical component of that 0.20. So we'll look at that here in just a second when we plug in. Right? But again, at this stage, it's just plugging everything in. So 1/2 my spring constant of 250. It's been stretched 0.2 meters, right? So 0.2 squared, plus my mass of that first block, which is 30, right, for the hanging mass, times 9.8, times my gravity, and again times the height, which was 0.2, because that's how far it's been stretched. Okay. So then on the right-hand side, I've got 1/2. The total mass of the system would be 50 kilograms, times the velocity, which I don't know. And then the mass of object 1, which is 20, times gravity, times the height, which again is not the 0.20, but it is 0.20 times the sine of my angle, which they give me is 40. Right? That would be my change in height as it goes up the ramp. So in any case, this point you've got all of the measurements except your final velocity, which you don't know. So my final velocity would be 1.24. Right, so 1.24 meters per second is what I end up getting when I calculate all this. Again, a little bit of a mess, I know. It takes a little bit of practice to get used to it, but it's really just working with energies. I'm just identifying all of the energies that act on either block, both before and after the system. Right, so that's the only thing I'm working with here. And I do want to make sure you guys are all comfortable with this type of question. So anyway, if you do have questions on it, let me know. The last question here, question 9, I actually want to cover this one in class. So I don't think I'll post this on the video right now. I think I will go ahead and just discuss this question in class. In particular, part B is very, very tricky. So I want to talk about that in person with you guys when I see you. So I won't throw this in the key. If you are curious, the answer for part A, if you at least want to check that, the displacement there is 1.46 meters. So if you want to check that part, go for it. But I'll talk about part A and part B when I see you guys again in class.